A Boeing 777 slams into the runway at 160 miles per hour, 350 tons of aluminum and fuel crushing down on just 12 tires. The rubber instantly heats to 500 degrees Fahrenheit. Smoke billows. The wheels spin from 0 to 150 miles per hour in half a second. And here's what should happen next. Those tires should explode like bombs. But they don't. In fact, in the entire history of modern aviation, tire explosions on landing are so rare they make headlines when they occur. How is this possible? The answer involves the gas you're breathing right now, engineering that defies logic, and a secret about airplane tires that most pilots don't even fully understand. Those wheels aren't filled with what you think. And the reason they survive? It breaks every rule you know about pressure, heat, and physics. Ready to discover why airplane tires are one of aviation's most underrated miracles? Picture this. An Airbus A380, the world's largest passenger jet, descends towards a runway. This flying giant weighs 560 tons. That's heavier than a fully loaded freight train. And in 3 seconds, all that weight will transfer from wings generating lift to 20 tires, each no bigger than a truck tire. The weight? That's the easy part. Firstly, the speed differential. The aircraft touches down at 170 miles per hour. But the wheels? They're not spinning at all. Complete standstill. In less than half a second, friction alone must accelerate these 300-pound wheels from 0 to match the aircraft's speed. The energy transfer is violent, so violent that the tires instantly heat to 500 degrees Fahrenheit, hot enough to melt lead. The rubber actually vaporizes on contact. That's the smoke you see. We're literally watching the tire destroy itself in real time. But here's what's truly mind-boggling. Each tire experiences 38 tons of weight. But that's the static load. Dynamic forces during touchdown spike to nearly double that. We're talking about 75 tons of force per tire. That's equivalent to parking 50 cars on something the size of a coffee table. Now add lateral forces. Crosswind landings can put the aircraft down at a 15-degree angle to the runway. The tires must grip, flex, and guide this massive momentum back to centerline without tearing themselves apart. Airplane tires? They're inflated to 200 psi, 6 times the pressure of your car, 14 times the pressure of a basketball, twice the pressure in a champagne bottle. These aren't tires. They're controlled bombs. Yet Emirates Flight 231 landed in Dubai this morning with its A380 touching down at 175 miles per hour. All 20 tires survived. Same thing happened yesterday and the day before. In fact, across 100,000 commercial flights today, virtually every single tire will survive its landing. But here's the secret that changes everything. Those tires aren't filled with air at all. These tires are not filled with compressed air. That would be catastrophic. Instead, they are pumped full of pure nitrogen, the same element that makes up 78% of the air you're breathing right now. But in airplane tires, it's concentrated to 95% purity or higher. Why nitrogen? The answer reveals engineering brilliance hidden in plain sight. Remember those 500-degree temperature spikes during landing? Air contains 21% oxygen. Heat plus pressure plus oxygen equals fire. In the 1980s, several aircrafts suffered tire explosions during landing. The investigation's conclusion was chilling. Compressed air at high temperatures can literally combust inside the tire. Mexican Airways Flight 940, November 1986. A DC-10's tire exploded on touchdown. The oxygen-fed fire burned so hot it melted through the wheel hub. The aircraft skidded off the runway. That incident changed everything. But nitrogen's advantages go way beyond preventing fires. Here's where physics gets fascinating. Water vapor. It's in compressed air, and it's a silent killer of aircraft tires. At 41,000 feet, outside temperature plummets to minus 70 degrees Fahrenheit. Water vapor in the tires freezes into ice crystals. The tire pressure drops dramatically. Then, during descent, these ice crystals melt. causing pressure variations that can lead to blowouts. Nitrogen is bone dry. Zero moisture content. The pressure stays constant, whether the aircraft is in Death Valley or above the Arctic Circle. But wait, it gets better. Nitrogen molecules are larger than oxygen molecules. They leak through rubber 40% slower. That means more consistent pressure over longer periods. For an airline operating hundreds of aircrafts, that translates to millions in reduced maintenance. A single Boeing 747 tire properly inflated with nitrogen can handle 500 landings, 500 times enduring those impossible forces we just discussed. Regular air? You'd be lucky to get half that. Singapore Airlines discovered this the expensive way. In 2001, they experimented with using regular compressed air on their cargo fleet to save costs. Within 6 months, tire replacement rates doubled. Maintenance costs exploded. They switched to nitrogen and never looked back. The precision required is extreme. Too little pressure, and the tire flexes excessively, generating heat that destroys it from within. Too much pressure, and it can't absorb the landing impact, potentially exploding on contact. The sweet spot? Exactly 200 psi for most commercial jets, maintained within a 2% margin. But even nitrogen-filled tires inflated to perfection would explode on landing without the next secret: the extraordinary engineering hidden inside every aircraft tire. Akron, Ohio. Inside Goodyear's aerospace facility, a machine stretches an aircraft tire to 8 times its normal size. It's filled to 800 psi, 4 times normal operating pressure, while engineers in blast shields watch from behind reinforced glass. The tire expands and expands. At 1,200 psi, 6 times operating pressure, it finally explodes with the force of a small bomb. This is called burst testing, and every new aircraft tire design must survive pressures that would destroy a bank vault. Cut open an aircraft tire, and you'll find something that looks more like body armor than rubber. 14 layers of specialized materials, each with a specific purpose. The outer tread, that's not even rubber. It's a synthetic compound developed by NASA that can withstand temperatures from -100 to +500 degrees Fahrenheit without losing elasticity. Beneath that, steel cables. But not just any steel. We're talking about cables stronger than those holding up suspension bridges. Each tire contains nearly a mile of these cables, wound in precise patterns calculated by supercomputers. One pattern handles vertical loads, another manages lateral forces. A third prevents expansion under pressure. The genius is in the angles. Those cables cross at exactly 45 degrees in opposite directions, creating what engineers call a bias ply construction. When pressure increases, the cables lock against each other, preventing expansion. It's the same principle that allows spider silk to be stronger than steel. Here's a shocking fact: aircraft tires don't have inner tubes. That technology disappeared in the 1960s. Instead, they use an inner liner made of butyl rubber, the same material used to seal spacecraft. This liner is so impermeable that nitrogen molecules, despite being incredibly small, take months to leak through. Michelin's factory in South Carolina produces a single 777 tire every 30 minutes. The process requires 250 pounds of materials, 32 different compounds, and curing in massive presses at 300 degrees for 4 hours. The cost? $5,000 per tire. But here's the incredible part: retreading. After those 500 landings, when the tread is worn, the tire doesn't get thrown away. It's sent back to the factory, inspected with ultrasound and X-rays, and given new tread. A single tire casing can be retreaded 7 times. That's 3,500 landings from one tire structure. The testing these tires endure is borderline sadistic. Dynamometer testing spins them to 300 miles per hour for hours. Brake testing heats them to 1,000 degrees. Impact testing drops 40-ton weights on them from 10 feet. One test actually shoots bullets at inflated tires to ensure they deflate safely rather than explode. Boeing's 787 Dreamliner introduced something revolutionary: tire pressure monitoring systems that transmit real-time data to the cockpit. Pilots can see exact pressures for all 10 tires. A 3% deviation triggers a warning. A 5% deviation grounds the aircraft. British Airways learned this importance tragically. February 2008, a 777 landing at Heathrow had one tire underinflated by just 15 psi. The uneven load caused the adjacent tire to overheat and explode during taxi. No injuries, but the aircraft was grounded for a week. Yet even with all this engineering perfection, things still go catastrophically wrong. But here's the classified data the airlines discovered. The real cost isn't buying tires, it's managing them. American Airlines runs a tire control center that tracks 8,000 tires across their fleet in real time. Each tire has a serial number, a complete history, and predictive analytics forecasting its replacement date. Why such obsession? Because a tire failure doesn't just cost $5,000 for replacement. If it happens away from a hub, you're flying in mechanics, equipment, and replacement tires on a special flight. Cost: $50,000 minimum. If it delays departure, add $30,000 in passenger compensation and missed connections. If it damages the aircraft, you're looking at millions. Southwest Airlines figured out something brilliant. By standardizing their entire fleet to Boeing 737s, they used just one tire type. Inventory costs plummeted. Mechanics need training on just one system. They even negotiated bulk purchasing agreements, saving 30% per tire. But the real revolution is retreading. Remember those 7 retread cycles I mentioned? Here's the economics. New tire, $5,000. Retread, $800. Over the tire's life, that's $5,000 plus $5,600 in retreads for 3,500 landings. Total cost per landing, $3. $3. That's what stands between 300 passengers and catastrophe. The future is already here, and it's wild. Airbus is testing tires with embedded fiber optic cables that detect internal damage, invisible to any inspection. Boeing is experimenting with self-healing rubber that can seal small punctures automatically. And in Japan, Bridgestone is developing tires that change their tread pattern based on runway conditions. But the Holy Grail? Airless tires. NASA and Goodyear are developing spring tires, made from memory alloy coils that can deform and return to shape indefinitely. No inflation needed. No blowout possible. The catch? They're currently 10 times heavier than traditional tires, making them useless for aviation, for now. And about the future, predictive deflation. Lufthansa is testing AI systems that deliberately reduce tire pressure by 2 to 3 psi based on specific runway conditions, weather, and aircraft weight. This microscopic adjustment can extend tire life by 20% while improving braking performance. The numbers are staggering. The global aircraft tire market, $2.1 billion annually. By 2030, with air travel doubling, we're looking at $4 billion. Someone has to make, install, inspect, and recycle 500,000 aircraft tires every single year. So next time you're gripping your armrest as your plane touches down, remember what's really happening beneath you. Tires inflated with nitrogen to 200 psi. Pressure that would destroy most materials are instantly accelerating to 170 miles per hour while supporting 350 tons and heating to 500 degrees. They're not just surviving this violence, they're doing it 500 times, in rain, snow, and crosswinds, on rough runways from Lagos to LaGuardia. Those black rubber circles are engineered with the same precision as a spacecraft, tested to destruction, and monitored by global satellite networks. The question isn't why airplane tires don't explode on landing. The question is how humanity engineered something that turns the impossible into the routine, 100,000 times every single day. What surprised you most about aircraft tires? Have you ever experienced a tire incident on a flight? Drop your story in the comments below. Because while we obsess over engines and wings, it's these unsung heroes that truly bring us home.